This is the one which I call method of the finding of inverse proof. It's not really it's a schematic of the proof. It's a very great idea. It explains why we do it that way, and it's very easy to present. That's why I use it as at the beginning of today's lecture. So I'll start with a reminder what we do when we find an inverse. So we have a matrix, right? A of size n times n. N is an integer, and we often need the entries of that matrix. That's why I will choose a name for those entries. Little a will be my name. So the inverse, the way we introduced it 2 days ago, it was another matrix, again of identical size, n times n, such that it acts as a cancellation factor with my a. That's what I mean by that. It cancels my matrix into the identity. It's a very useful property if you solve for something, if you would like to get rid of a factor, of a matrix factor. That's where identity comes handy, because it cancels. Right. So in order to understand the method, in order to understand the motivation or the reasons for the method we use, we need to look at my matrices from the column point of view. From the column point of view. What I mean by this is that, what I mean by this, I'd like to, well, my intention is this, right? I need to find this B. That's my inverse. It is unknown to some extent, right? We're looking for it. That's the inverse. This B, it's a matrix of size n times n, so it has n square entries. So strictly speaking, we have n square numerical unknowns we're solving for. That's exactly what the process of finding the inverse is about, finding those values, finding those unknowns, the entries of your inverse matrix. I will be looking for those unknowns in this schematic by grouping them into columns. That's exactly what I've done here. You see, I split my B into columns, this x1, x2, xn. They represent the columns of my matrix. They are unknowns. And I'm looking for them, because the moment I know them, I know my inverse. I will also split into columns the identity matrix. These are known columns. In fact, we have a reserved notations for those columns, right? This is something which often comes with the name standard basis in Rn. And we reserve a special name for that basis, this E, boldface E1, E2, En. Yeah, that's how we look at that basis. It's the vectors. Sorry, each E sub j is a vector which filled with zeros except for one place, the jth place, and that's the place which has 1 in it. These type of vectors, we had a special name. You had a special name for them in the first year. You call them standard basis in Rn. If you look at the identity matrix in a column way, columns of the identity matrix will be standard basis in Rn. That's exactly what this line tells you, or tells us. Right. So the key to the entire schematic is matrix multiplication, of course. I mean, we have to look. I will address only one of these relations, because if you remember on Wednesday, I confirm with you that if you have one of these relations, AB equals identity, you can safely assume that you have the other relation as well. So we only need to find B, which works with one of those relations, and I will choose AB. So the key to everything is this line. It's a short line, but actually it condenses a lot of information, and it relies on your very good, very comfortable understanding of matrix multiplication. Because what it says is this: when you multiply two matrices, the way we do it, the way we refreshed on Wednesday, you can do this multiplication in a column, per column way, as long as you split into columns the second factor. See, that's what this line says. It tells you if you multiply A and B, and if you split your B into columns, the result will be as if you multiplied every column individually by A. It's a deep result. It's a structural result of the matrix multiplication. It underlines a lot of results in matrix theory, and you probably saw it before. If you didn't, that's a big omission. This is the first time, then this is a good time to see it and remember it. It helps in many proofs. If you accept this, if you don't, you have to spend some time with this. But if you accept this, then what happens next is this. We just take the left-hand side, we take the right-hand side, and we split this into individual relations, right? If I aim to achieve that this AB equals identity, in the column sense, it means I aim to achieve that the first column equals to the first column. Second column equals to the second column, and so on. And that's exactly what I said here. That's what I aim to achieve. First column equals to the first column. Second column on the left-hand side equals to the second column on the right-hand side. And you do it for all of the n columns. The last relation will be nth column equals to the nth column. The moment I wrote this in these individual column relations, the moment you do this, and if you look closely at these n relations, what do you spot? Well, I hope you see here n different systems of linear equations. This identity individually, it's a system of linear equations. Unknowns in that system, components of this x1 vector, components of the first column of my B. This is another system of linear equations. And you have n of those. This is the last one of those. We know how to solve each such system, right? What we do, we build augmented matrix for that system. And for that system, it will be the matrix which has A on the left-hand side, and E1 on the right-hand side. You build the augmented matrix for the second system. That's the shape of that augmented matrix. A on the left-hand side, E2 on the right-hand side. You do it for every system in a sequence. Last one will be like this. And then you embark on solving these systems, right? Your process will be finding the chain of row operations which convert each of these n augmented matrices into row echelon forms. If you practiced well with the row echelon forms, especially if you listen to my lecture on Monday, you remember by now that the sequence of these row operations, it depends only on the left-hand side. It doesn't really matter what sits on the right-hand side. Remember those parametric examples we did with the b's on the right-hand side? Those b's, they may be anything, but they never affect the choice of your row operations. The only content of your augmented matrix which affects the choice of the row operations is the left-hand side. And all of these have the same left-hand side. So if you start solving each of them individually, you will soon realize that each of them requires the same row operations. And hence comes your efficiency trick. Why would you do it n times then if it's the same row operations? We would do it in one go. And we build this one big augmented matrix where we collect all of the right-hand sides to the right of my A, and we do one set of those distinct row operations we need. And that's the reason, all of these columns, when you collect them on the right-hand side, they will end up just the identity. And this is the reason for that method of finding the inverse we know. Because we effectively, what we do in that method, we solve n systems simultaneously. And we can do so because all of those systems, even though they have different right-hand sides, they have identical left-hand sides.